Hello everyone, thank you very much for joining me today. My name's Shaun Lawrence and I'm here to share with you one of my favourite recipes for brewing beer, which involves writing some .NET code, throwing in some relatively cheap IoT devices and hardware components, and then we mix it all together with some raw ingredients with the aim of creating a great tasting beer. Okay, let's go ahead and proceed with the content. I would first like to begin with a wise old proverb, which is give a person a beer and they drink for a day, teach them to brew and you give them a hangover for life. So I plan to walk you through my introduction to brewing, the general brewing process, and then onto how we can automate elements of this through .NET and IoT. So my first brew was back in 2007. I bought an extract kit of lager, mixed the ingredients together in a bucket, similar to this one you can see in the slide, wrapped it in a towel, thinking it would need some extra level of insulation, and then I placed it by our airing cupboard for roughly 2 weeks. And this was actually a surprising success. What I didn't fully appreciate at the time, though, was this success was due to the ambient temperature. It was spring after all, and it was actually ideal for a lager yeast to thrive. And subsequently, my next attempts to brew during the summertime were not as successful. So this led me to go off and learn a little bit more about the brewing process. So the brewing process, typically it will start with cleaning. We want to make sure that everything is sanitized and rinsed. And as a good friend of mine tells me, cleaning typically makes up 75 to 80% of the brewing process. So there is a lot to it. Then we make the wort, and wort is basically a liquid made from grain or adjuncts, which is intended to be turned into beer by yeast. And this is a big simplification. The wort making process is actually quite involved. It entails mixing, heating and boiling, adding hops at varying times, adding malt, chilling and aerating. Now I've left this as a single bullet point because it is entirely possible to skip this step by purchasing a malt extract. Then we mix the ingredients together. Fermentation is the step after that, which involves leaving the brew untouched for up to 2 weeks, and we want to maintain a consistent temperature for this stage. Then comes carbonation, which involves either leaving it in your keg or carboy, or transferring it to bottles. Typically, you want to put it in a vessel that you can serve from at this stage. So I've got a little keg that has a tap in it, so I typically leave it in the keg. And you typically add a little extra sugar or sugar solution at this stage to excite whatever yeast is left and carbonate the brew. And we want to maintain a consistent temperature for this stage, which is typically a little bit higher than the fermentation stage. And then finally, one concept that is certainly common in home brewing is to cold crash the beer at the end. And this involves rapidly dropping the temperature down to refrigeration temperatures with the aim of forcing any yeast or leftover bits in the brew to sink to the bottom. A lot of my journey into brewing has been influenced by the book that you can see on this slide, so it felt fitting to give it a shout out. The book is called How to Brew by John Palmer, and it really is, as the subtitle suggests, everything you need to know to brew great beer every time. So to quote John here on his top 5 priorities for brewing great beer, and this is a prioritized list from top to bottom, the most important factor is keeping things clean. Now, don't worry, this isn't going to turn into another clean architecture talk, but you do want to make sure that your yeast is the only microorganism in your brew. After sanitation, we have fermentation, and for healthy fermentation, good temperature control is key. Yeast are living organisms, and their activity is controlled by temperature, much like us humans. Essentially, for proper yeast management, you want to make sure that you're using the proper quality and quantity of the yeast. Then there's the boil. The ingredients are cooked during the boil. So as with any recipe or meal that you might make, if you don't cook the ingredients correctly, you won't have the intended outcome. And then finally, we have the recipe. And John is referring to the list of ingredients and how they blend together to make a great tasting beer. And I do not disagree with him, but I use the term recipe as a set of steps that can be followed. So from this list, I've tried to look at what could be automated, at least in quick wins, and then ultimately I would like to expand to more moving forward. So sanitation is the top priority, but not necessarily the easiest thing to automate. We'd have to be pumping solution around. But I didn't want to cross this off the list. so what I've done instead is consider it a requirement or a constraint of the system. And constraints on a project like this are certainly a wonderful thing for myself. They help with me try and avoid scope creep. So what I've interpreted this to mean is that a homebrew setup needs to be easy to clean. Therefore, we want to reduce the number of components that are exposed to the brewing process. Then there's fermentation, and this is goods temperature control, and spoiler alert will be the primary focus of the code examples you see today. Then there's yeast management, and as I mentioned, this mostly falls into buying good quality yeast and using the right amount. Now, you could technically automate half of this by setting up a direct debit to your favorite supplier. The boil does also involve some level of temperature control, but I find the ingredients don't always need the exact same time. If you compare it to a packet of pasta you might buy off a supermarket shelf, I always find that the boiling time on the side doesn't actually match reality. Therefore, I prefer to keep this a manual task so you can manually inspect it. And finally, the recipe, and this ties in with using IoT, because the device doing the actual work does not just do one thing at one setting. These values need to change throughout the course of the brew process. This is our recipe. We covered sanitation in the last slide, so let's take a look at the next highest priority, which is fermentation. You can see on the slide here that the two distinctions I made here, which is between a lager and an ale, and they typically have different temperature ranges that they like, and also they like to thrive in different areas of the brew. So the lager yeast thrives on the bottom of the brew and likes to operate between 45 and 55 degrees Fahrenheit or 7 and 13 degrees Celsius. And the ale likes to feed on the top, and they like to thrive between 15 and 22 degrees Celsius or 60 and 72 degrees Fahrenheit. But temperature control is easy, right? You could actually log onto your favorite online retailer now and buy these three things and have a working temperature control system. You could take the smart plug in a heated blanket and control whether it's on or off through using a smart thermostat. And this in theory would work, but it would be largely inefficient, which we will cover shortly. One way to make things more efficient, though, is to create something called a fermentation chamber. And the aim of this is actually you end up regulating the temperature inside the box. And an ideal candidate for this is a fridge, because it actually already provides decent insulation, as well as having the ability to cool at the end for the cold crash. So this is what I've set about building. And in order to do that, the first thing I've opted to do is measure the liquid temperature. So that means actually getting a probe into the brew, which comes back into our first point of sanitation. We need to make sure that it's easy to clean. Then once we've got the ability to monitor the temperature of the thing we want to regulate, we can then react to it and influence it. So we introduce a heating element, which will then be able to turn on and off dependent on whether the brew is at the right temperature or not. And then also we can introduce a fan to circulate the heat, because we don't want to sit the brew on top of it and just cook the bottom of the brew. We want that to actually allow the heat to circulate around the chamber. And then finally, I've opted to measure the ambient temperature. And the main reason for this is if you know it's 10 degrees outside and you're heating, you know that if you overshoot, the temperature will actually naturally drop. You don't have to turn on the cooling element in order to come back down. So I mentioned that a fridge is an ideal candidate. I've sadly not got permission to modify our house fridge or garage fridge. So I've been building a working prototype, which is this thing you can see on screen. And this is a powered cooler box that I've taken apart and put some components on. So you will be able to see that on the top, we've got an LED unit powering the board, as well as some relays, a Peltier heater cooling element on the middle, display on the right, and then inside we've got a temperature probe and also a heater element. Okay, so we've covered a fair bit of the what, and hopefully the why is obvious. Let's now take a look at the how. I've opted to use the F7 Feather, or V2 up here, which is a board built by a company called Wilderness Labs. And the board kickstarted back in 2018 by some ex-Xamarin and Microsoft employees that wanted to take their knowledge of the Mono runtime and make it work on low-powered devices. It comes with some really nice features like BLE and Wi-Fi support directly on the board, as well as levels of encryption, and the ability to interact with all the common protocols that you would expect from a machine control board. It has a whopping, though, 32 meg of RAM, which compares to this Pentium 200MX from 1997. Now, this is not to put the board down, but hopefully to just draw attention to the limitations that come with building applications for IoT devices. As a .NET developer myself, I've been afforded the luxuries of a beastie web server or a desktop PC that has gigabytes of RAM. We don't have that luxury here, so we just need to be mindful of that. Now, Meadow is a full-stack IoT development environment, and on this slide you can see a bit of a breakdown of how it's structured. The boss will start at the bottom, so the bottom layer is the Meadow OS is built on top of the NutX micro real-time operating system, which is an open source project you can view. The code is then built to run on the Mono runtime inside of the Meadow operating system. Then the layer above is the Meadow.core, and this is typically where you probably start to interact with things. And these are the low-level drivers, so you would be able to open an analog input port and read the voltage coming in. And then the layer above that, we've then got the Meadow Foundation, and this provides pre-built drivers for specific peripherals. So the example on the slide here is the BME 680, which is a temperature humidity detector. But there are many other options that you could utilize. It is possible to develop for these devices through either Visual Studio Code for an extension, or the command line interface. And the developer docs give you a very good introduction on how to get started. So we won't be doing that today, but I would thoroughly suggest you check out the link. Okay, so the first piece of hardware that we're going to interact with is an ambient temperature sensor, like you can see on screen, and we can wire it up to the board much like this. Essentially, you wire up between positive and ground, and it will then return you a voltage based on the current temperature. And this, like I say, this will be the first interaction, so let's go and actually take a look at this in code. So what you can see here is we've got a class called ambient temperature monitor. Essentially what we do is we create a new instance of the ambient temperature sensor, tell it which analog input pin to receive the voltage on, and we also tell it a known type. There are options if you don't know that. If it's not a supported type, you can choose for custom, and then you can actually provide a bit of calibration values in order for it to calculate the temperature reading. And then you can see when we actually want to read it, we just call read, and that will then give us a literal that gives us Celsius or Fahrenheit, depending on how we want to use it. Okay, back to the code, back to the slides. So the next thing, just before we proceed to the next slide, is just to highlight the fact that this works fine for ambient temperature. If we considered putting this into liquid, you can see the pins are exposed, so it instantly shorts out and we'd not get a valid reading. So for this reason, we are going to opt for a very different type of sensor. And the one that I've got opted for here is what's called a PT1000, and it's a resistance temperature detector. So rather than its voltage changing, its resistance changes based on the current temperature. And this, the PT100, the 100 stands for its resistance is 100 ohms at 0 degrees Celsius. Now, in order to interact with this, we need to use one of these little breakout RTD converters, which essentially boils down to wiring it in, and then we communicate to the board through SPI to tell it to basically enable monitoring and disable monitoring. And you'll see here, this is a rough idea of how we can then actually wire it up against the board. So what we'll do is now we'll jump over to the code again, and we can have a look at how this one works. Now you should see that this looks remarkably similar, but one key point to note is that this MAX 31865, which is the board, is not directly supported by the Meadow Foundation. However, I have opened a pull request to enable support, so this has been structured in a way that would benefit others. And what you'll see is actually we have to tell it a bit more of the lower level stuff. So we need to tell it create a spy bus instance so we can communicate to it. And then the rest you can just call read, much like before. But this hopefully then goes to show, if we can click into this, you'll be able to see that it's entirely possible for you to create your own drivers in C# and convert them across. So actually this was converted from a C++ library, but there are also C# libraries out there that could have been used. I only realized that later on in the day. And you'll see that basically we have to read and write registers. That's how it works for the spy bus. Okay, right. So now that we've got the ability to monitor the temperature, we can now influence it. Now, this is the first time we need to consider more power than the Meadow board can provide. I don't believe I covered it earlier, but just to highlight, the Meadow board can output 3.3 volts and 5 volts. But the heater element that I've purchased for this runs off 12 volts DC, and ultimately the fridge that I've got Grand Designs on runs off 230 volts AC. So we need to be able to bridge the gap between our low-powered board and a higher-powered piece of hardware. And how we can do this is through something called a relay, which is essentially a programmable switch, which allows us to open and close a second circuit. If we go and have a look at this in code, what we will see is we can simply create a class called relay, or an instance of a class called relay, tell it the pin, so that's the digital pin that tells you whether the circuit should be open or closed, and then you do just tell that state to be open or closed. And this will then allow you to turn the heating on or off, as you can see in these two classes. Excellent. So, job done. We've implemented the ability to read the temperature and influence it. Now, if you recall back in the heated blanket approach, I mentioned that it was inefficient. We've actually just recreated that. So let's take a look at why. So one of the key inefficiencies here is because when we are heating up to a target temperature, what will happen is once we reach that target temperature of, say, 20 degrees, I think 21 on this chart, we'll turn the heater element off, but there will be residual heat left in there, which means we will continue to be heating. And then once we then start to drop that downwards curve, when we then reach the target temperature as we're dropping, there will be time for the heater element to kick in and actually to actually start affecting the temperature of the brew again. Therefore, it's not very efficient because you'll result in this temperature oscillation. So let's take a look at how we can potentially solve this. Now, one such way is through something called proportional integral derivative, which is a rather complicated looking algorithm that will allow us to deal with the error and actually calculate an efficient way of managing our temperature control. Now, this is not an advanced lecture talk, so we won't be going into the detail of this, but we will certainly know how to learn how to use it. So what it does is it's built on top of something called control theory. And an analogy I like to use is driving a car. I mean, ultimately, cruise control features in cars use this, but I like to use the human element of it. So if you imagine you're driving a car, you're coming onto a slip road, or you're on a slip road coming onto a motorway or a freeway, you know that you're expected your target signal, your target speed would be 70 miles an hour. You will know that the output, you're currently doing 50 miles an hour. Therefore, the actual might tell you that you need to put your foot flat down 100% of the way onto the accelerator pedal. As you periodically look down at your speed, the speed that you are doing, you will then potentially adjust your position, knowing that how fast you're speeding up. So if you were to look down after 2 seconds, so you're doing 55 miles an hour, you might stay flat out, but by the time you reach 60 or 65, you then might start to lift it up, because your expectation is not going to reach 70 miles an hour and then lift your foot completely off and then put it back down again, because you'll recreate that oscillation, but in terms of a rather bumpy ride. That's something that you would avoid, and that's your human brain applying the PID algorithm. It's also worth mentioning that PID is also used in lots of heating control systems in the world. So typically the heating in your house or even the coffee machine, they all rely on this algorithm. And what happens then once we apply this algorithm, you will then see that you can achieve a much smoother ascent, and that you will always overshoot and undershoot slightly, but you will then be able to account for errors and then actually ideally create that flat line there. Now, of course, there will always be bumps in the road, such as someone opening the fridge door to have a look, check that the beer is still happy, but we can then adjust for that and handle that and then reascend to the target temperature. Okay, so let's go and have a look at this in code. And what you'll see actually is there really isn't much to this. So the Meadow library provides us with the standard PID controller class, and we can configure it in certain ways. So we tell it what the PID values are. Now there's no magic one size fits all for these values. You will need to tune this, which ties into the last property that's being set there, output tuning information. If you turn this on, you can essentially log all of the information out into a CSV format and then upload it to online tools that will allow you to tune that your PID to get the ascent and the smooth line that you want. And then you can also then set the output min and max to allow you to whether you want to limit the amount of full power. You may only want it to go to 80%. And then in order to perform our read, what we do is we tell it the actual and the target, and then we ask it to calculate the control. If you look in here, this is where actually that algorithm on the slide is actually being implemented. And we don't have to worry about this complicated math because it is provided for us. Okay. If we now move on, the one thing to consider now, though, is what we've done is we've implemented the ability to provide an amount of power to our heater element, but we've only got a relay which can either be on or off. Now we could go and redesign the circuit, introduce something like a controllable MOSFET, but it's late in the day. We don't want to redesign the circuit now. We want to ship something. So what we can do is we can use another piece of technology, which is called pulse width modulation. And this is actually how LEDs remain bright without burning out quickly. And in fact, if anyone has taken a photo and seen dark horizontal lines, this is caused by interference between the frequency at which the light is oscillating and the speed of the rolling shutter in the camera. There's two key components to PWM. You've got the duty cycle and you've got the frequency. So the duty cycle is a percentage of how much it's on for. So if we take the example of 75% on the bottom, and if we said there's a frequency of 1 hertz, that's 1 second, every second, that will mean that the output will be off for 1/4 of a second and on for 3/4 of a second. So if we then take this into account, what we can do is then go and look at some more code. And I don't believe I covered it on the slides, but the Meadow board does support 12 hardware-based PWM ports. However, I always find with any system, if you've got a limitation like that, someone may ask for a 13th or a 14th. So what I've opted to do here is to implement it in code rather than the hardware level, because then that means there are fewer branches. If we did need a 13th or a 14th, you don't have to say, well, if I've reached my limit, use the soft port rather than the hard ports. We can just drive it all through the same code. And what it essentially lets us do is we tell it the port that it's controlling, and then we tell it the duty cycle and the frequency. So in this sample, it sets it up. The duty cycle is 100% and the frequency is 10 hertz. So, or 1 hertz, not 0.1 hertz, which is 10 seconds. Which then allows us to, what we do is then when we call our PID controller to calculate the output, being the power level, we can set that to the duty cycle. So if we're given a duty cycle of 0.6, so 60%, our heater will be on for 6 seconds and off for 4 seconds. Okay, so this currently concludes the examples that I was hoping to show you. What I would like to highlight though, before I finish off, you should see that while there is device-specific code, so we've got the Meadow support, a bit of Pi-based work that I've been playing around with, there is also the workings of a .NET MAUI-based application, as well as a web API, and also some shared code as well, which goes to highlight some of the wonders of using .NET on all of the layers, is that we can then share things like the data transfer objects that would go between them. Good. So let's go and have another look at our slides. Yes. Okay. So the code examples that I just mentioned cover each of the individual components that you can see on this screen. Now, the talk is titled "If .NET Brewed Beer," and the primary focus of this talk has been around how we do that at the IoT level, so the low level on the device. But I have wanted to prove a kind of a fully integrated system. So the expectation is that the IoT device will make HTTP requests or possibly MQTT once I've finalized that detail. But ultimately, it can communicate with a web API that is currently hosted on a Raspberry Pi, along with an Aspire dashboard, because I want to test out the latest and greatest features. And then a .NET MAUI client that will then communicate with that app with that website as well. So you can then see that the current process of the brew, or you could even create recipes on the mobile device. So hopefully that gives an indication as to what's possible in this space. And the one key takeaway that I would like to highlight is the fact that I'm not using Windows in any part of this development process or deployment. So you'll see we've got the Meadow board running .NET code. That could in theory also be a Raspberry Pi. We've then got a web API website and Aspire dashboard running on a Raspberry Pi that the IoT device communicates with, and then a .NET MAUI based application. Now, of course, .NET MAUI can deploy to Windows, but I'm using it on my Mac and my iPhone. So therefore, like I say, it goes to show the power and flexibility of .NET in the modern age. Okay, so I would like to just wrap up. I want to say cheers. Thank you very much for coming to listen to me ramble on about beer and IoT. I hope it's been fun. I've certainly enjoyed it. I'd love for you to reach out and let me know whether you're working on hardware specific things, what type of beer you like to drink. Please feel free to reach out and let's connect. Excellent. Thank you very much.